All right, this is your 5.2, section 5.2. We're going to talk about linear transformation, the properties of linear transformation. And especially we're going to talk about kernel and image of various transformations, right? So image. So the function f, the input is x and then output is y. We call it one-to-one, just like the regular function. We call it one-to-one, or we call it, the new word here is injective. So if your output is same, so f of u, f of v is same, that implies that always u and v has to be same, right? So in other words, if u and v are not the same, you can do the same thing. You can be, if they are not the same, that means f of u and f of v, that's the output, not going to be same too. So that's a one-to-one. So I mean, you can think about like a if it is like a y equal to x square function, right? Y equal to x square. So here, if you have two different input, like a -2 and 2, you have two different input, it has a one output, same output, 4, right? And that's not one-to-one, right? And the set of output values function, the set of output value function is subject to the codomain. So you can see that they are the part of the codomain. So they are the codomain is called the image of the function. So image of the function is, this is your y, that's your codomain. This is your image. We call it a range too. If the image of all y's of the function, if the image of all of y's, the function is said to be onto, or it's called surjective. Okay, just like if we look at the example here, again, your x is input. There's like a transformation. We use the transformation. So when x is input, your output is all y's. So this is here. So this is not surjective because there is a one is not, that's not part of the input, this one, right? So that's not the image of any input there. So that's why it's not a surjective. But this is one-to-one because it goes one-to-one. So this is one-to-one and surjective in the second one. This one is one-to-one and it's surjective, right? Because one input has two different outputs. So, I mean, this is not even a function, is it? Because you have one input has two different outputs. That's not a function. So two different input has one output. That's not one-to-one. So it's not one-to-one, right? And then this could be a surjective, right? Because it's all the range, like all of the outputs are included there. So this is not surjective because this is not mapped to anything, right? From anyone, it is not mapped to anyone. So, but this is here. This is onto or surjective. This is one-to-one. This is one. This is two different input has one output. That's not one-to-one and not surjective. This one is also called injective, right? All right. Just review that terms. It might be helpful here. Let's see. If your T is a transformation from V to W, be a linear transformation, right? From space V to space W, and the image of this V is like an image of T. That's what we call. And if the image of T is the subspace of W, so image of C is always going to be subspace of W. T is surjective if and only if the image of T is everything with a W. All right, so image of T is exactly same as W, then that's called surjective. Rank. What is the rank? The dimension of the image of the linear transformation. So after you, if I do the transformations like this, so AX, you look at that, and then you're going to find the, so all the image of the linear transformation is the rank. Okay, we're gonna talk about that in a second here. All right, so here for matrix M by N, A is associated to the linear transformation. So we talk about that, right? The linear transformation. So matrix vector multiplication is a linear transformation. So what happened is when I multiply by A matrix to a vector V, it transformed to different vector, right? That's the linear transformation. So for all x's, this is input, and T is the column space of A. So what does that mean, right? So image of T is the column space of A. What is the column space of A? I'm gonna show you an example in a second here. The pivot columns of A, form the basis for the image of T. All right, that's what we're gonna talk about in a second here too. So again, one more time, the rank of T is exactly the same as dimension of image of T or dimension of column space of A, which I'm going to explain you in a second here. But what is the column space of it? What is the dimension of column space of A? Is you look at the pivot columns. Number of pivot columns on A is the rank, is the column space of A. The dimension of column space of A, which is the dimension of image of T. That's the same thing over here. Okay, so this is the key part. So you look at the A, change into row echelon form, and find the row echelon form, reduce row echelon form, and look for the number of pivot columns. Right, the number of pivot columns is the rank of T, or this is the column dimension of column space of A. Right. So I think I have an example here, and a quick example here. Again, this is your A matrix. I change into row echelon, reduce row echelon form. So you do the Gaussian elimination. If you do that, you're going to get that. So you have, let me change the color here. So you have this column, and these columns are, these two columns are pivot column. Right, so that means your rank of a matrix A is 2. So rank of a matrix A is 2. Again, that's exactly same as dimensions of columns of A, right? And dimensions of image of T. So again, when you write down the column space of A, okay, let me erase this one again. Let's write down column space of A is, I would write down, if you have like X, Y, Z, I would write down like this. I would write down X. This is a linear combination of 1, 1, 1, right? Plus Y, 1, 2, 1, plus 1, 1, 1, right? So if I all the linear combinations. All right, let's say Z here. All right, so this will produce all the column, but this is not quite, because this can be all the columns can be basis for A, but are they really linearly independent or not? You need to figure out, right? According to here, our work here, they are not all linearly independent. Only the 2 of them are linearly independent. So that's why we only take 2 of them. So column space of A is a span of these 2 vectors, not all 3 of them, right? So only 2 vectors spans for the column space of A. Okay. And then since they are linearly independent. Okay. All right, we'll continue this one.